Okay, so in the last few lectures I talked about how we discretize in time when we have a time-dependent partial differential equation. And we talked about things like that when you have a parabolic equation, there's this diffusive effect, and so it's a second-order spatial differential operator, but then you have only a first-order time derivative, and these things are a little bit imbalanced, and when you, let's say, wanted to do something like an explicit time-stepping method, that doesn't lead to anything good. You have to choose a time step that is so small that it's impractical. And so for parabolic equations, we argued that we needed to have an implicit time-stepping method. On the other hand, if you had a hyperbolic equation, so let's say a transport-dominated problem, if it's a first-order equation, or if you had something like the wave equation, you wanted to have an explicit time-stepping method because you can choose the time step appropriately. So the time step would be proportional to, let's say, the mesh size. That's what we want from accuracy reasons, and that also guarantees stability for the usual schemes that we have. So for both second and first order hyperbolic equations, you would want to have an explicit time-stepping method. So what I want to talk about in this lecture is, what do you do if the equation that you have does not quite fall into these neat categories? It's neither hyperbolic nor parabolic. It has parts that are, let's say, some transport-dominated aspects, some diffusion-dominated aspect. And how do you approach these sort of things? What are the ideas that you can use to find a time discretization that is appropriate for these sort of questions? So this is lecture 30.25. I'm going to talk about the advection diffusion equation. I'm going to talk a little bit about, let's say, more general questions, and the sort of methods that I want to talk about are called IMEX, that's short for implicit explicit, operator splitting methods, and some other ideas that fall into this general category. So just to rehash this, if you had a parabolic problem, and the typical parabolic problem would be the heat equation that I've written down here, so it's du over dt, that's the first time derivative, minus the Laplacian of u, so that's the second spatial derivative, equals some right-hand side. So for these parabolic equations, we had argued that we want an implicit time-stepping method. So it needs to be implicit, or we have an impractically small time step. For hyperbolic equations that are second order, so something like the wave equation, where I have second time derivatives minus the Laplacian, we argued that you want to have an explicit time-stepping method, or at least that you can use an explicit time-stepping method, which is, of course, far cheaper than an implicit one. And the same thing that I didn't talk about in the previous lectures, but the same kind of argument also applies if you had a first-order hyperbolic problem, and the typical prototypical equation that we look at is the transport equation, which says that the rate of change plus some advection terms, so there's typically a, let's say, wind speed, for example, and so that's my beta, that's a vector, dot the gradient of the solution, so that would be the derivative of u in direction beta. That is used to model, let's say, transport of pollutants in air, so that's a typical first-order hyperbolic equation, and for these two, the same argument applies, namely that we want to have an explicit time-stepping method. So the questions that I want to investigate in this lecture and in coming lectures is, what do you do if the equation that you have does not fall into any of these neat three categories? So you have an equation that mixes these terms, for example. And let's say, what are the common approaches, what are the ideas that we use to address these questions? So let me introduce a prototypical equation that we want to investigate and think about how to solve. So I'm thinking of an equation that has this transport equation as the first part here, and then I add to it a diffusion term, okay, so minus Laplace u. And so oftentimes, let's say, if we wanted this to be realistic, there would be a factor in front here that, let's say, says how much diffusion I have. But that is not material, it's not important to the purpose of this lecture. You can think of it being there if you want to. So this equation appears in all sort of circumstances where you have both transport and diffusion, and there are many examples of this. So if you think about, let's say, pollutant transport in the air. I live in College Station, which is about an hour and a half north of Houston. Houston has a lot of oil refineries. So oil refineries, like many industrial facilities, do give off some pollutants. Some of that, of course, is transported away by the wind. In the summer, we have winds from the Gulf of Mexico, which blows basically from Houston straight up to College Station here. And the equation that you would use to describe how these pollutants are transported along from the sources across the country are, you have to take into account that the wind transports things along without changing it. So that would be the advection part of it. But then also, gases diffuse. So even if you have a point source, let's say a chimney, for example, there's material that comes out and is transported along by the wind, but let's say it's not transported along just along this one line, but it starts to diffuse. And the further away you get, the wider this plume becomes. That happens in gases, that happens in water. If you think about, let's say, putting a drop of ink into water, it's going to diffuse. There are many other aspects as well. So I'm talking about substances diffusing within the medium, but the same happens with energy or temperature diffusing, all of these sort of things. So that's a pretty common equation for people to want to solve. So it has both this advection term here and then a diffusion term. And if you look at this from the perspective of the previous few lectures, this term here would suggest that we use an explicit time-stepping method, and this one here would suggest an implicit time-stepping method. So what do we do? So we could, of course, solve an implicit or use an implicit method for this. And that would be a totally reasonable thing to do because, let's say, we need an implicit method for this one anyway. So you could argue that maybe the additional cost to treat this one implicitly is not very large. And that's not wrong. I'm going to show you something on the next slide, what that means in terms of, let's say, the matrices that are involved. But so let me first introduce one of the ideas where we really treat these terms differently. So I start with this equation here, okay? And then I'm going to discretize this in time. That means I'm going to replace du over dt by un minus 1 divided by kn. Un is the current solution at time step n, un minus 1 is the previous solution, and kn is the length of the time step over here. And so when I said that I'm going to treat this explicitly here, that means that I'm going to use un minus 1 here, but over here I'm going to treat it implicitly, and then that means that I'm going to use un here. And as is common when you think about, let's say, how to solve this, so I already know un minus 1. So I'm going to take this term over here to the right-hand side, and the same with this one here. I'm going to put that on the right-hand side, and then I'm going to multiply the entire equation through with kn. And so what I have on the left, the un's are the things that I want to solve for, and everything on the right-hand side I already know. So that's how I conceptually think about these equations. And let's take a look at how this looks like. So I have, if I discretize this, I'm going to get a mass matrix here. After, you remember, so I get a mass matrix because I multiplied with a test function. I expand u in terms of the coefficients times the test functions. So I'm going to get the mass matrix here, and minus Laplace gives me plus the Laplace matrix, right? And I multiply the Laplace matrix by the time step, which is presumably small. So I'm going to get something like mass matrix plus kn times the Laplace matrix. And that turns out to be a really nice matrix to invert because the Laplace matrix has a condition number that grows like h to the minus 2. You remember that from the discussion when we looked at the eigenvalues. So the condition number of the Laplace matrix grows like h to the minus 2. But I multiply it with k. K is, the time step is at the same size as the mesh size, so k is like h. So the condition number of k times a is on the order of h to the minus 1. So it's much more moderate in terms of condition number. And then I'm going to add to it the mass matrix, and the mass matrix has condition number 1, right? So I'm just going to shift the entire spectrum of k times a to the right by 1, basically. So that's a matrix that is symmetric and positive definite. It's not particularly poorly conditioned. It's really easy to solve this one. So that's using this implicit for diffusion and explicit for the advection leads to something that's actually quite nicely solvable, and every unpleasant thing happens on the right-hand side. Imagine for a second that I had chosen this one to be implicit as well. Then I would get an additional term on the left side here that has the advection matrix. And the advection matrix has the disadvantage that it's non-symmetric. So I would lose some of the properties of this matrix that I have to solve on the left, and it would make things a little bit more complicated. So I couldn't use the conjugate gradient method, for example. I would have to use something like GMRES or BiCGSTAB. So I really want this to be explicit because it makes my life a lot easier. So that's sort of the idea of an implicit-explicit split. The IMAX methods actually approximate this in some way. So I start with this equation here, where I have the time derivative. I choose this term explicitly, this term implicitly. And I'm going to split this into 3 individual parts. So you can think of something like this. So I want to write down an equation where I start with un minus 1, and I also use this for the advection term, and I'm going to compute a solution that I'm going to call un advection that in essence solves only an equation that only the advection equation and neglects all of the other terms. It has no right-hand side and it has no diffusion term. And I'm going to call the solution un advection. And I'm going to do the same thing with the diffusion term. I'm going to solve an equation that only has the diffusion, and I'm going to call the solution after one time step un diffusion. And I'm going to do a third time an equation that has no spatial derivatives at all, that just has the right-hand side here. And I'm going to call this un source. And if I add up these increments here, so these are this term and this term and this term, you see that they, so if I bring everything else to the right-hand side, you see that it's exactly this term plus this plus this. So the result is, in fact, approximately equal to this one here. And the only difference is that in the diffusion part, here I have un diffusion as the thing that I solve for in the diffusion term, whereas up here in the original equation I really have un, the complete solution. That's the only difference between this one and adding the components together down here. So to make this a little bit clearer, let me multiply each one of these equations by kn, and I'm going to call these differences here delta un advection, for example. So delta un advection really is just k times the diffusion term, the advection term. For delta un diffusion, it is really just the Laplacian times the time step times un minus 1 plus the delta, right? That's the implicit part of it. And the same thing for the right-hand side. And then I can write my solution for these IMAX schemes, for the approximated approach, as un equals un minus 1 plus the 3 deltas. So that's sort of how we approach these sort of things, that instead of solving one equation implicitly, I think of solving 3 equations that take individual aspects of the equation into account. So why would I want to do this? That has a number of advantages. So for the equation that I looked at, this is actually the way I think, let's say, if I had to implement it, I really would implement it like I said down here, where I really have to solve mass plus k times Laplace. That's an easy matrix to invert. So I really would implement it like this. These IMAX schemes split this up, and why would you do this? So it has the advantage that I can run these 3 solves for the advection part, for the diffusion part, and for the right-hand side. They're completely independent of each other, right? I can, if you look at this, delta un advection does not appear in this equation here, nor in the equation over here. And the same is true for delta un source and delta un diff. So each one of these equations can be solved at the same time, concurrently, if I want to. And oftentimes when people use these sort of splittings, they do this because the effects they want to model are, let's say, physically very different. So you can think of, let's say, a situation where you have airflow around an elastic structure, let's say a bridge. Then if you use these sort of splittings, then you would be able to solve the airflow part with an aerodynamics code and the structure part with a structure code. So you can use separate codes for these sort of these things, and that gives you flexibility. These codes don't really have to know much about each other. They can run at the same time and solve their own part of the problem, and at the end you just add them together. I should have said that, so these the source contribution, so that's this thing over here, this K and F, if that is structurally, let's say, related to the advection, then I could have equally well, of course, put it in here. If it is structurally related to diffusion, I could have put it in here, and then I need only two solves. This method, of course, incurs an error, right? So if I go from up here to down here, I've made an approximation, namely that I don't have un here, but I have only un minus 1 plus delta un here. There is an error involved in this, and I can generalize these sort of schemes to higher order that ameliorate that error. So that's how we think about these sort of schemes, these IMAX schemes. I want to give you an alternative that's a little bit older, that dates back probably to the 60s or maybe early 70s. And these schemes are called operator splitting schemes. And the difference is that the IMAX schemes, they treat all of these terms concurrently. So I can solve all of them at the same time, and at the end I add things together. Whereas operator splitting schemes solve these three different problems one after the other. They too can treat transport explicitly and diffusion implicitly if you want to. And I'm going to introduce them by just showing you a flowchart. So what I really want to solve is this equation up here. Okay? And let's say I first solve an intermediate problem that I'm going to call u in advection, where un minus 1 is already given, and I'm going to only solve an advection problem where I put in the previous solution, so it's explicit, into the advection term. And what comes out of it is u in advection. And then instead of concurrently solving u in diff, I'm going to use the solution that comes out of this. So this u in advection, I'm going to use that as the starting point for a diffusion step, also of length kn. Okay, and now I can really treat this completely implicitly again. So u in diff, that's the same u in diff that I have here. And what comes out of solving this thing here is a u in diff. And I can put this in as the starting point to solve a third equation, out of which comes u in source, where I'm just solving for the right-hand side. And u in source is what I'm going to call, here, this is where I want to be. U in source, that is the end result of my time step. So un is the result of first taking one full time step with only the advection, and then one full time step with only the diffusion, and then one full time step with only the source. This is what we call the least splitting. So it takes one full step with each one of these terms. I'm going to contrast the least splitting later with the strength splitting. So when I learned about this scheme, I was initially confused by the fact that we take full time steps with each one of these equations. I thought you should take, let's say, a third time step with advection, and a third time step with the diffusion, and then a third time step with the right-hand side. But that's the wrong view. You really have to take a full time step, because you need to take one full step of the advection effect. And then, of course, you have to also take one full step with the diffusion effect, and then you want to somehow add them together. And the fact that you do this one after the other, it's not like we do, let's say, the equivalent of 3 full time steps. We really just do one full time step, because in the first time step I have no diffusion, or let's say in the first equation that I have to solve I have no diffusion, in the second I have no advection. Let's say it's not 2 times kn of the effects that I consider, but I really only consider 1 kn, one time step of it all. So the fact that I solve 3 time steps with a time step kn really only accounts for 1 kn of all 3 effects at the same time. So that's what the least splitting is. And so if I want to look at this, I can do these 3 increments independently. I can't do them concurrently anymore. I have to wait until the previous step is done. But I can still do it with separate codes, for example. And as before, if I want to, I can put the source effect into one of the first 2 steps if I want to, and that works. So the Lie scheme is only first order accurate in the time step size. And that often limits the accuracy that I can get out of this scheme. But it's easy to generalize into something that is called the strand splitting, which is second order in time. And so that makes it easier for me to get higher accuracy. And I want to introduce to you how this works. And I'm going to do this in a simple equation or a simple example. So let's say, for example, I had an equation that models the reaction of 3 species. So I have species A and species B, let's say hydrogen and oxygen, and they react to water. Okay? So my solution, that should be a vector, consists of UA, UB, and UC, and the equations that I can write down to is that the rate of change equals, well, the rate of change of this reaction, okay? And then they also diffuse. So at every point in my domain, I have certain concentrations. There is a reaction going on, but let's say the reaction that happens at one point, if I create water at one point, it's going to diffuse through my entire domain eventually. And typically for these sort of things, diffusion is much smaller than this. So if you want to put in a little epsilon or something small in front of it. For chemical reactions, the right-hand side terms typically look like this. So I have a product of UA and UB, which means, let's say, UA is a concentration, UB is a concentration. In order for a reaction to happen, I need to have both A's and B's there. And so the likelihood that a reaction happens is proportional to the product between the 2 of them. And then I have a proportionality constant. K has nothing to do with the time step, it's just a proportionality constant. And a negative sign, because when a reaction happens, I reduce the amount of A, and I reduce the amount of B, and I increase the amount of species C. So when you look at this equation, then there's a spatial process here, right? That's a diffusion, and there's a local process that happens only at, so it has no spatial derivatives in it. It's just, if you want to, an ODE. And typically, you would have different codes that specialize in each of these 2. So you would have, let's say, a finite element code for the diffusion part, but then you would have an ODE solver that solves the chemical reactions. And that may not be necessary for this little equation here, but oftentimes when you, let's say, simulate how gasoline burns in an internal combustion engine, you have hundreds of species, and these equations become very, very complicated, and you would have specialized codes that solve the chemistry behind that solve the reactions. So you really want to use these sort of splittings where you can use your finite element code for the diffusion, and then that's for, let's say, the first half of the step, and then for the second half of the step, you just run the ODE with a specialized code. And so let me show you how this looks like for this Lie splitting, for this operator splitting approach. So let's say my first part of the step, my first increment is going to be, I start at my previous solution, and I'm going to compute a U star that only solves the diffusion part and does it implicitly, okay? And then I'm going to do another full time step worth of only the reactions. So I could write this as, let's say, U star star minus U star over Kn equals f of something. But in reality, all I really need to do is I need to solve this ODE from time Tn minus 1. And I'm going to start this at U star. That's the diffused solution, okay? So I'm going to start this at Tn minus 1. And then I integrate this up with my ODE solver up to time Tn. Okay, so my U star star, that's the reaction ODE. I'm going to solve that to Tn, and that's what I'm going to call the solution here. So that's what the Lie splitting would do. And you see that in a finite element simulation, for example, this here would be something that I have to do at every node of my mesh. But I can do it independently because there are no spatial derivatives. So I can just solve an ODE at every node of my mesh from time Tn minus 1 to time Tn, and that's going to be the solution at the end of the time step. And if I want to, I can reverse the order of these two. That doesn't matter. In this case, the error is exactly the same. Let's say the error order is exactly the same if I first did the reaction and then the diffusion. Like I said, this is the error here is proportional to the time step kn, the error that comes from the splitting approach. If you used a strength splitting, you can get this error down to k squared, to the square of the time step, and the strength splitting looks like this. So I'm going to first do a half diffusion step. So I'm going to do this for 1/2 of the time step. And then I'm going to solve a full time step of the reaction. Okay, that's exactly the same as before. So I'm going to get a u star out of this, out of the diffusion step. That's going to be my starting values for the reactions. Then I'm going to integrate this up to Tn, and that's going to be my u star star. And then my u star star is going to be the starting point for another half diffusion step of length kn over 2. That's what we call the strength splitting. So half step, full step, half step. And that turns out to be proportional, or the error that I introduced from the splitting turns out to be proportional to the time step squared. And as before, I can revert the order of these substeps. So I could do first a half reaction step, then a full diffusion step, and then another half reaction step. And it turns out that for this particular case, it might actually be useful. But the error analysis shows that at least asymptotically, the error order is exactly the same, regardless of whether I go first with diffusion or first with reaction. So that's the strength splitting. I want to comment at the end about a couple of things that might increase the accuracy. So in both the IMAX and the operator splitting schemes, we somehow have to discretize the time discretization here. And the simplest approximation that I've used in all of the previous slides is in essence just the Euler approximation, or the BDF1 approximation. It comes by many different names, which means I'm going to replace this time derivative by un minus 1 divided by the time step k. That's not the only choice that I have. I could also use something like this. So it's 3/2 of un minus 2 un minus 1 plus 1/2 un minus 2 divided by k. That is also a finite difference approximation of the time derivative. And it turns out to be 1 order more accurate. And I can, if I have un minus 3 and un minus 4, I can find other weights here that allow me to do something similar. So the fact that I wrote down all of the previous slides by just using the first order approximation here has more to do with the fact that I wanted you to see these equations as clearly as they really are. I wanted you to understand the concept behind this. But in reality, if you wanted to implement this in a high accuracy solver, you would go with something like the BDF2. BDF stands for backward differentiation formula, or BDF3. And the other part that I want to talk about is when you think about explicit terms. So go back to this equation here where I had the advection term and the diffusion term. So we approximated this advection term explicitly. So there was a un minus 1 over here. But that's not the only choice. So explicit really only means that I don't have un appearing in these equations, right? So explicit means that I have un minus 1 and un minus 2, un minus 3, previously known solutions. Whether I write it as un minus 1 or I do a linear combination of un minus 1, un minus 2, un minus 3, that's a different question. It's still explicit as long as it does not involve un. And so there are other options, for example, this one here. So I could, instead of writing un minus 1, I could start at un minus 1 and I extrapolate that using the derivative that I compute from the previous two time steps, right? So un minus 1 minus un minus 2 divided by k. That's the time derivative times the length of the time step. So this whole thing here is something like an approximation of un. I just extrapolate from the previous two time steps. And that gives me a more accurate solution because I have something that is almost like un in this term here, but it's still explicit because I don't have un in that place. So I can get higher order accuracy from this. So to sum this whole lecture up, if you have equations that are not either purely hyperbolic or purely hyperbolic. There are many different ways how you can treat this. So typically you want to treat certain terms explicitly and others implicitly. And you want to treat different physical effects separately, sometimes running different codes. And there are many different approaches how you can do this. And there are many different ways how you can achieve higher order accuracy by extrapolating or by using higher order finite difference schemes. I hope you get the idea of how we play with these sort of terms to achieve what we want to achieve.